morning. Welcome to our discussion of alkanes as part of our study of organic chemistry. Alkanes are also called paraffins. Now, why are they called paraffins? They are called paraffins because of their low affinity for other reagents or other compounds. So because of their low reactivity or low affinity for other substances, they are called paraffins. The general formula of alkanes is CnH2n plus 2. The first member of the alkane series is called methane. Methane has other names. It is also called fire damp. And then a more popular name for it is marsh gas. So marsh gas, fire damp are alternative names for methane, whose molecular formula is CH4. Alkanes are generally saturated, that is to say, in an alkane, the carbon-to-carbon bonds are usually single all through. In terms of hybridization, every carbon atom in an alkane molecule is sp3 hybridized, and that gives alkanes an overall tetrahedral shape and a bond angle of 109 degrees and 28 minutes. But this is often written as 109 degrees or 109.5 degrees. So in many texts, you are going to see 109.5 degrees, but the actual value is 109 degrees 28 minutes. Then the reaction that alkanes undergo, the type of reaction that they usually undergo is substitution. One last thing. Alkanes are the only family of organic compounds that lack a functional group. So should you get that question, what is the functional group in alkanes? Please say they have no functional groups and you'd be correct. Moving on, what are the basic properties of alkanes? First, in terms of their physical state, alkanes can exist in all three states of matter. The first four members of the alkane series, that is carbon 1 to carbon 4 members, whose names are methane, ethane, propane, and butane, are gases at room temperature. Then, from the fifth member to the 17th member, we have liquids. These ones are liquids at room temperature. That's from pentane to heptadecane. Liquids at room temperature, but they are volatile liquids. And then from C18 and above, we have the solid alkanes. So those members are solids, but they are low melting solids. In terms of their reactivity, we already said that they have low reactivity. They are not as reactive as other groups of organic compounds like the alkenes and alkynes. Those ones are way more reactive. So the reactivity of alkanes is generally low, and that is attributed to their being saturated. So because of their saturated nature, they do not react very much. Then in terms of applications, many alkanes are used as fuels, especially the gaseous ones and the liquid ones. Like natural gas, a very popular fuel, is chiefly methane. It contains more of methane, up to 85-90%, as some put it. So up to 85% of natural gas, if we get a sample of it, is methane. And then what about domestic cooking gas, which is called petroleum gas? Yes, that contains propane, butane. So you see that the gaseous hydrocarbons are commonly employed as fuels. Then for the liquid hydrocarbons, they are commonly found in things like petrol, diesel. So the common fuels we use, kerosene too, they contain many of these liquid alkanes. A related family of compounds are the ones we call cycloalkanes. The cycloalkanes, yes, are saturated too, in terms of the fact that all their carbon-to-carbon bonds are single, But in terms of their general formula, they share the same general formula as alkenes, which is CnH2n. Also, cycloalkanes are otherwise called naphthenes. So the naphthenes are the cycloalkanes. It's an alternative name for them. Moving on again to preparation this time, there are various ways of making alkanes, and these include preparation from RCOOK. What does that stand for? RCOOK can be pronounced as potassium alkanoate. So it's not necessarily just the potassium alkanoates. We can use sodium alkanoates in some cases. So most importantly, we say they can be prepared from the sodium or potassium salts of alkanoic acids. Sodium or potassium salts of alkanoic acids. In that case, we'll look at two methods. We'll look at decarboxylation and we'll also look at electrolysis of this kind of compound. After that, we'll talk about what is called the Wurtz reaction. Then from the Wurtz reaction, we enter the Grignard synthesis, Grignard's method, and then hydrogenation as methods of making alkanes. So let's look at the first one, preparation from potassium alkanoates or sodium alkanoates. What would it involve? Well, the first step there shows that it could be by decarboxylation. Consider this popular reaction. CH3 COONA plus NaOH to give CH4 plus Na2CO3. Now in this reaction, what do we see? This is sodium ethanoate and it's reacting here with sodium hydroxide. Sodium hydroxide is called caustic soda. However, caustic soda has undesirable properties that could affect the nature of this reaction, such as it is deliquescent. So its deliquescence and the fact that it affects glass or attacks glass now could affect the outcome of this reaction, so that instead of using ordinary sodium hydroxide, which is caustic soda, we commonly use it in a mixture with quicklime. Quicklime is calcium oxide. Calcium oxide. So for this reaction, we don't use pure sodium hydroxide. We use sodium hydroxide mixed with quicklime. Remember, sodium hydroxide is caustic soda. So that when you mix it with quicklime, the mixture will be called soda lime. So in many texts, you hear that alkanes can be prepared by combining or reacting sodium alkanoates with soda lime. Here we don't use ordinary soda for the reasons I mentioned earlier. So this has given us an alkane, and the alkane there is called methane. Notice that the organic compound we had at the start had 2 carbon atoms, but the organic compound we have at the finish has 1 carbon atom. So the number of carbon atoms in the organic compound has reduced. Such reactions, where number of carbon atoms in an organic compound becomes reduced, will be referred to as decarboxylation. So decarboxylation, when it occurs during a reaction, we see that the number of carbon atoms in the starting material is greater than the number of carbon atoms in the final product. So this is one way of getting alkanes, very suitable for methane, and I'm sure this is the first reaction that many of us encountered in organic chemistry, the very first chemical reaction in organic chemistry. Now, for the second method, which is electrolysis. That method was actually described by this man, Hermann Kolbe. So we call it the Kolbe's electrolytic method. What is Kolbe's method about? Yes, as the term there says, it involves electrolysis. Now, if we take a salt written as RCOOK and we were to electrolyze it, of course, on entering solution, on dissolution in water, we expect that we have RCOO minus and K plus. From the basics of electrolysis, if this substance were to be electrolyzed, you would expect the K plus to migrate to the cathode, and this would migrate to the anode. Now at the cathode, it's either K plus is discharged as potassium or H plus is discharged as hydrogen gas. But remember, we want to prepare alkanes. It means therefore that our interest will not be in the cathode. What we'll be more interested in is what goes on at the anode. That is where our alkane will be produced, and it will be produced like this. So I'm going to write an equation now to represent the change that takes place at the anode. Remember that from basics of electrolysis, oxidation is what occurs at the anode, while reduction takes place at the cathode. And let's remind ourselves again, what is oxidation? This oxidation that we said takes place at the anode. Yeah, oxidation is electron loss, loss of electrons. So what happens at the anode can be represented as RCOO minus 2 moles becoming 2 moles of CO2 plus RR plus 2E minus. Now, here are 2 electrons that have been lost. They have been lost, that's why they're on the right-hand side. And when there's electron loss here, we already said that is oxidation. So this is oxidation occurring at the anode. This is 2 moles of COO, that appears there as 2 moles of CO2. Then we're left with 2 R's, which also appears here as RR. Now, RR in this equation simply stands for alkane. How is that so? Well, I'm sure you're conversant with the fact that R is a symbol used to represent alkyl groups in organic chemistry. So based on that, if you take 2 alkyl groups and add them together, you are sure to get an alkane. Consider this. If I add CH3 to C2H5, what do I get? C3H8. Is that an alkane? Yes, that's propane. So you can pick any 2 alkyl groups of your choice, and as you add them up, you are sure to get an alkane. So imagine that this reaction had been carried out with a specific compound, let's say potassium ethanoate. This is potassium ethanoate. If this potassium ethanoate had been our starting material, then it means that at this level, in place of RCOO minus, we would have had CH3COO minus. Your CO2 would still have been formed, yes, 2CO2, so that's 2CO2. You still would have obtained your 2 electrons, of course, electron loss, oxidation. But on this side, RR becomes CH3CH3, and CH3CH3 can be written as C2H6. So I have an alkane now. This alkane was produced where? At the anode. So in the Kolbe electrolytic method, 1, what kind of compound do we electrolyze? The potassium salt of an ester of an alkanoic acid. 2, at what electrode do we expect to get our alkane? At the anode. 3, what kind of reaction takes place at that anode? Oxidation. That's from basics. Then 4, what kind of alkane do we obtain? We obtain an alkane of the form RR. And usually, when this Kolbe's method is used, the alkane we get is an alkane that has even number of carbon atoms. So the carbon atoms could be 2, 4, 6, even numbers. All right, that's what we get usually by the Kolbe's electrolytic method. So that's Colby's method. Now imagine that under exam conditions, you are given something like this. Under exam conditions, maybe you are given question 3 as C2H5COOK, and then the rest of the question says, which alkane is produced if this compound is electrolyzed? In that case, you simply need to replace this formula with RCOOK, bearing in mind that the alkane you will get will be RR. So if you compare these two now, where's your R? C2H5. That means the product here will be C2H5, C2H5, which gives us C4H10. So the alkane will be butane. But if you choose to go stepwise, no problems. In that case, you'd have C2H5COO minus and what? K plus. Would we need to follow K plus to the cathode? No. Focus on the anode. So what reaction would take place at the anode? Oxidation, as usual, like this. It will be 2CO2, which is from here, 2CO2 plus C4H10 plus 2E minus. So this is a complete representation of what would happen should we use this compound in place of that. Now that we are done with the Colby's method, let's talk about the Wirth reaction. But in talking about the Wirth reaction, I would love to look at it side by side with the Grignard method because they share some things in common. So let's split our board in two now to talk about Grignard on one side and the Wirth reaction on the other side. Now for the Wirth reaction and the Grignard reaction, the first thing they have in common is the fact that each of them involves alkyl halide. So on this side I have Wirth, and on that side I have Grignard. Alright, so the Wirth reaction and the Grignard method. I said they both involve alkyl halide. So there's alkyl halide here, there's alkyl halide there. There's also anhydrous ether or dry ether on that side as well as on this side. So the two of them involve the use of alkyl halides. The two of them involve the use of dry ether as solvent for the alkyl halide. Then the last thing that must be present for this reaction is metal. So in this case as well, there is metal. So does it mean there's no difference at all between these two reactions? Well, there's a difference, and the difference is in the metal used. In the case of the Wirth reaction, the metal used is sodium, whereas in the Grignard reaction, the metal used is magnesium. So that for the Wirth reaction, we have something like this. 2 moles of Rx plus 2 moles of sodium in the presence of dry ether. So DE there is dry ether. I'm trying to manage or conserve the space there. So 2Rx combined with 2Na, what does that give me? It gives me RR. And what is RR? Alkane. Then we have 2 X's left here, right? Plus the 2 sodiums there. Together, they will give us 2NaX. So imagine this for a specific compound. Imagine in an exam on question 5, you were given C2H5Br plus 2Na in the presence of dry ether. What would we have as product? First, these your 2 moles of bromine from this compound will combine with those two sodiums so that I have 2NaBr. Then what is my second product? According to the upper line, it will be RR. So coming down here, it will be C2H5, C2H5. That means my other product here will be C4H10. So that's my second product for this reaction. And of course, that's the important product because what we are looking at is preparation of alkanes. Now, having seen this, it's so easy. We have made butane from ethyl bromide. Now, there's a relationship or a similarity between this Wurtz reaction and the Kolbe method that we have just considered. What's the similarity? Even numbered alkanes, RR. So just as Kolbe's method will usually give us alkanes with even numbers of carbon atoms, that is how the Wurtz reaction also gives us alkanes with even number of carbon atoms. But what about the Grignard method? See what happens under the Grignard situation. In this case, we have Rx, this time around magnesium, and then on the arrow, dry ether. Now, when Rx reacts with magnesium, the Mg does not just pick X the way sodium picked X here to form NaX. Instead, both of them will form something like an adduct, like they form just one substance that is represented as RMgX. That RMgX can be called an alkyl magnesium halide. So we call any compound that has that formula RMgX an alkyl magnesium halide. But please bear in mind that R is not necessarily alkyl. R may also be aryl. And what is aryl now? Aromatic alkyl, which is still alkyl anyway. So something like C6H5, which is phenyl, may occur here. So we have C6H5 MgCl, for example. It will still be an alkyl magnesium halide. These alkyl magnesium halides are otherwise referred to as Grignard reagents. Grignard reagents. So what is a Grignard reagent? We say a Grignard reagent is an alkyl magnesium halide. It is a compound of formula RMgX. We describe them as organometallic. Organometallic in that they are organic compounds that contain metal. Having said that, reaction between Rx and Mg does not give us alkanes straight up like these ones. Instead, when Rx reacts with Mg, we get a Grignard reagent. What can we do with the Grignard reagent? We can go ahead to dissolve it in dilute acid. When a Grignard reagent is dissolved in dilute acid or reacted with dilute acid, we get the alkane we desire. Okay, which means therefore that the Grignard method is like a two-step method of making alkanes, unlike the Wurtz reaction that is one step. One step in the sense that if Rx reacts with Na, we get our alkane all at once. But if Rx reacts with Mg, we don't get alkane. Instead, we get a substance that will dissolve in dilute acid to give us alkane. And that substance is a Grignard reagent. So dissolving a Grignard reagent like RMgX now in dilute acid, which is H2O with H plus, like that. That's dilute acid now. We get our products as RH plus MgOH. Look at that reaction. What is RH? What does RH stand for? RH stands for alkane, in that if you take any alkyl group and add hydrogen to it, you get an alkane, e.g. C2H5 is an alkyl group. If I were to add hydrogen to it, it becomes what? C2H6, and C2H6 is an alkane. So apart from RR, alkanes may also be represented as RH. If I were to take a specific example here, let's say I take CH3MgI. Now, if you look at this compound and compare it with the formula above, CH3 corresponds to this, Mg, then I would correspond to X. So this is a Grignard reagent. And how would this Grignard reagent be formed from this step? It will be CH3I plus Mg in the presence of dry ether. That would give us this. So that if this substance is now dissolved in water, dilute acid, we will get as product CH3, which is R, H plus this. So in that case, this CH3H is better written as CH4. And of course, the second product there is MgOH. Which halogen do we have? Iodine. Now, the beauty of the Grignard method is, unlike Colby and Wirth that gave us even-numbered alkanes strictly, the Grignard method can give us even-numbered alkanes as well as odd-numbered alkanes. So having mentioned these two reactions and having considered them side by side, the very last reaction is not one you commonly see in exams because it's way too simple, and that's hydrogenation. We mentioned it at the last. Hydrogenation. Hydrogenation of what will give us alkanes? Yeah, hydrogenation of alkenes and alkanes.